Okay, in this class I'm going to talk about Newton's laws and connected particles. So particles that are connected by a light inextensible string. So here we have a kind of a picture, and this is typical of a Leaving Cert standard question. It says two particles of masses 9 and 5 are connected by a taut, light, inextensible string. So the string doesn't stretch, it's tight, it's stretched tight, it doesn't stretch, it goes to its maximum length and then stays at that. It's inextensible. The string is light, it has no mass, we don't need to worry about the mass of the string. And they're passing over a smooth, light pulley. Smooth, no friction. Light, we don't have to worry about the mass is negligible. The system is released from rest. So I release this system from rest, and hopefully you see pretty much it's quite obvious what's going to happen. This string is going to pass over here, the 9 is going to pull down, and the 5 is going to move up. Okay. We're asked to find the common acceleration of the particles and the tension of the string. Their acceleration will be common because it's an inextensible string. There's no particle that's bouncing up or down or anything like that. So once one of them is moving at a certain rate, the other will be moving at the same rate. We'll find also the tension in the string. So the method is this, and this is really important when we're talking about connected particles, that we draw separate force diagrams for each particle. And I emphasize that each particle in any problem always gets its own force diagram. We think about the direction of acceleration for each particle, for each separate diagram. Different diagrams can have different positive directions. Develop a system of equations and solve. So it's fairly straightforward once you see it done once or twice. So let me go through the example. So this is the same question, I've just made it a bit smaller so I can squeeze stuff in here. Force diagram for the 5 kilogram particle. So I'm going to just draw the 5 kilogram particle like so. Remember, it's just a box and there's two forces at work. And see if you can think what they are, you know. One of them is the weight of the particle. Remember we said the weight of anything is always its mass times little g. And the other force that's acting on the particle is this pulling force from the string, which we call a tension force. So that's the force diagram for the 5 kilogram particle. Those are the only forces at work on the 5 kilogram particle. I'm going to draw a force diagram for the 9 kilogram particle. Again, its weight is acting downwards, in this case 9g, and in this case the tension still pulling upwards here. One thing I want to do is I want to think about the direction that these particles will accelerate. So because the 9 mass is greater than the 5, that means the 9 kilogram particle is heavier than the 5 kilogram particle, and you would imagine that's going to make the 9 kilo mass go downwards and the 5 kilo mass go upwards, and the pulley essentially rotate around this way. That's the way I'm thinking about it. So what I'm going to do is I'm going to say, because I think the acceleration is upwards for the 5 kilogram particle, I'm going to call that an up positive system. And because I think the acceleration is downwards for the 9 kilogram particle, I'm going to call that a down positive system. Now, if you guess wrong, that's not the end of the world. You'll just find out things work out with the wrong signs. But do take a second to think about the direction of acceleration. From these force diagrams, we're going to develop two force equations based on Newton's second law, which says F net equals ma. So the net force is mass times acceleration. So the net force, if this is an up positive system, I'm going to look at the 5 kilogram mass first of all, the 5 kilogram mass. The force equation for that mass, F net, well, the up force is T, the down force is 5. So the net force is going to be the positive force T, subtract that 5g. And that's going to be the mass, which we know is 5 kilos, times the acceleration. So there's my first equation, T minus 5g is equal to 5a. My second equation comes from my second force diagram here, from my 9 kilogram mass. In this case, I've said the downwards is the positive direction. So the down force here is 9g. The up force, which will be the negative force, is the t. So 9g minus t will be my net force. And then we have mass 9 times the acceleration. So what we have here is two equations. Two equations, you know, you can call that one equation 1 maybe. Call this one equation 2. And we need to solve that system, which you've hopefully looked at lots and lots of times. So let me finish this off up in this area up here. So t subtract 5g. So I'm going to take equation 1, which says t subtract 5g is equal to 5a. And I'm going to take equation 2, which says 9g subtract t is equal to 9a. And what I'm going to do is I'm going to use the addition property of equations, which says if equal quantities are added on both sides of an equation, then the two sides remain equal. So we're going to add these two equations together, adding 9g minus t on the left here, adding 9a on the right. And what happens is kind of nice, you know, 9g added to negative 5g, well that's just 4g. But t added to negative t, well they will cancel out. And 5a added to 9a, well that's going to be 14a. And now to solve for a, to find the acceleration of the particles, I just divide on both sides by 14. A is going to be 4 over 14 multiplied by g. And that will simplify to 2/7 of g. Okay, my units, meters per second squared. Okay, so that's my acceleration. The acceleration is 2/7 of g meters per second squared. The tension, well, to find the tension, I take either of these equations. Now let me look over here. If I look at equation 1, which is this equation here, and if I make the tension the subject of that formula, well, T is going to equal to 5a plus 5g. And we know what A is. A is 2/7 g. So I get 5 times 2/7 g plus 5g. So 10/7 g plus 35/7. I think it's going to be 45/7 of g. And this is a force, that's going to be newtons. So that's my tension. Okay, so there's my little calculation for T. My final answer for T in there is 45/7 g newtons. My acceleration is 2/7 g. Okay, so the method for these particular types, where it's just two particles hanging on either end of a string that's going over a single pulley, is pretty much always the same. Draw separate force diagrams for each particle. Think about the direction of acceleration for each particle and make that direction positive. Different force diagrams can have different positive directions. Develop a system of equations and solve. So this force diagram had an up positive direction, this one had a down positive direction, because that's the direction I thought acceleration would take place. For the 5 kilogram, this is the direction I thought acceleration would take place in for the 9 kilogram. Okay, once you have your two equations, just solve those things like your simultaneous equations from junior cert. Okay, I'm going to leave you with a question then. I'm going to flip over the page and I've got 6 separate systems here, and the question says which systems will have equal acceleration. So give those a go. See if you can find the acceleration of each of these systems, and we'll go through this the next day. So notice here 16 and 8, difference of 8, 8 and 4, difference of 4, 4 and 2, a difference of 2, 2 and 1, difference of 1 between those two, 12 and 8, a difference of 4, 12 and 4, difference of 8. Okay, so perhaps it's the differences that decide the rate at which they accelerate, or, you know, notice 16 is double 8, 8 is double 4, 4 is double 2, 2 is double 1. 12 is 1.5 times 8, and 12 is 3 times 4. So will that have any effect on the system? So work out step by step, draw separate force diagrams for each particle, decide which direction you're calling positive and negative, come up with your force equations based on those things, and solve the system. Okay, so give those 6 a go for the next day, and I will go through a solution. Okay.